Next topic we're going to be talking about is soil mechanics analysis. There are 6 topics included with this portion of the lecture. We'll be talking about pressure distributions, effective and total stresses, shear stress, lateral earth pressure, compaction, and consolidation. So pressure distributions and effective and total stresses will kind of work together and be almost one topic. Shear stress is not specified on the exam. However, it needs to be covered to talk about some of the other topics that we're going to be looking at. But this will just generally be an overview for you for soil mechanics. So looking at pressure distributions basically work from this equation right here. And so we have our vertical stress equal to our unit weight times our height, which this height could be, if I wanted to look at 2 feet below the surface, it would be 145 times 2. However, for this example, we're going to be looking at the bottom of this clay layer, so it's going to be 145 pounds per cubic feet times 5 feet, which brings us right here at 725 pounds per square foot. Since we're not increasing the load, this load will remain constant throughout the entire remaining 2 layers till we get to the bottom. So this will be 725 pounds per square foot of pressure that's being placed on this layer. Additionally, the sand layer right here is also putting pressure down here at the bottom as well. So this will be 124 pounds per cubic foot times 12, which brings us right here at 1488. And so that 1488 will continue on down to the bottom of the clay layer. And then similarly, we also have the 105 pounds per cubic foot times 15, which gives us 1575 pounds per square foot. And so when you add all these up, we wind up getting our actual total stress. And so the total stress at the bottom of the clay layer is 3,788 pounds per square foot. So that is a lot of stress. And so that's one of these things we'll be looking at with pressure distributions. But the idea with the pressure distribution is just the fact that you need to understand the shape. So as you go through one of these layers, the pressure is going to increase. However, once you're through that layer, that pressure remains constant and is just added to the pressure from the next layer to actually get whatever the pressure is at that point. And so if I wanted to figure out what the pressure was here in the middle of the sand layer, I could come right over here and figure out what this point is at 6 feet below the crushed rock layer. And so this kind of gives you an idea that as you go through, the pressures are going to increase. And so none of these triangles will have the same slope. However, if it does, it's just a little bit misleading, just from the fact that making shapes in PowerPoint isn't all that easy. So what this is going to wind up being is the slopes will be changing. It's just a matter of you understanding that. So when you actually calculate the pressure at a certain point in the layers, you kind of understand that. So this is with a soil structure that has no water table involved in it. However, when we start adding the water table into it, it changes things, because I'll have our total stress right here, which remains the same, and then I'll have what we call our pore water pressure, which winds up being 62.4 pounds per cubic foot times height. And so starting here, this is the first point where we're going to start having that load. And so that load will continue all the way to the bottom of the clay layer, and that'll wind up being 1,435.2 pounds per square foot. And so that'll be our pore water pressure. And so to actually calculate our effective pressure, you wind up taking your total stress and subtracting your pore water pressure, which will give you, at the bottom of the clay layer, a pressure of 2,352.8 pounds per square foot. And so the easier way to actually solve this, if you need to figure out what the pressure was right here in the sand layer, instead of calculating all that, you can use this equation right here, which is the unit weight minus the unit weight of water times the height, and that'll be the effective stress in one of these layers. However, just so you know, you only use the unit weight of water if it's below the groundwater table. So you wouldn't use it for the crushed rock layer here, you would just use the unit weight. And you'd also use the unit weight for this sand layer right here, this 4 feet section. Then you would start using the pore water pressure for this 8-foot section of sand and for the 15-foot section of clay. So just keep that in mind as you go through that. So now that we're talking about shear stress our shear strength is in soils depends primarily on the bonds in the aggregate. And so there's two sources of shear strength. You have cohesion, which is independent of stress, and then you have frictional resistance, which is dependent on stress. Essentially, what that means is this shear strength is present without any load on it, versus this one requires some sort of load or stress be placed on it for the frictional resistance to actually provide shear strength. And so kind of the way you're going to want to look at this is with cohesion. Typically, you're looking at very cohesive soils like clay will have high cohesion, and then clay has zero frictional resistance. Whereas something like gravel or something will have high frictional resistance but kind of low cohesion. So it kind of works that way. It's kind of proportional the next topic we're going to be getting into is shear stress. So shear strength for soils depends primarily on the bonds between the aggregates. So there's two sources of shear strength in soils. You have cohesion and you have frictional resistance. Cohesion is stress independent and frictional resistance is stress dependent. So the way I would consider this is without any stress or any load placed on the soil, we'll still have shear strength from cohesion. However, without a load, you won't have any frictional resistance. So once you start adding a load, you start getting more stress on that soil, so you start getting more of this frictional resistance. Another thing to consider is when you start talking about cohesive soils, they have high cohesion but practically zero frictional resistance. So something like clay will have a value for cohesion but have zero value for friction, versus a gravel will have high friction but no cohesion. And so they're inversely proportional in a way. But shear failure occurs when the stresses in the soil are such that the aggregates slide or roll past each other. And so with this, the aggregate has very good interlocking characteristics. You have very good frictional resistance and shear strength. Versus over here, as you can see, there's now a failure because all the aggregate is basically sliding across there. And so there's actually a failure plane associated with this. So this is kind of what this last bullet is hinting at. So shear failure, this is what it visually looks like, and this is kind of what good cohesion and frictional resistance will look like. So when we actually start talking about shear stress, we're going to get more into the kind of more circle again. So we have the Moore Coulomb failure criteria, which is basically this failure zone up here. And so with the Moore Coulomb failure criteria, a material will fail at a critical combination of normal and shear stresses, which is indicated by this point right here, and not at the maximum shear or normal stresses, i.e. the soil is not going to fail here at the maximum shear or here at the maximum normal stress. It's going to fail at some combination right here at some sort of friction angle. For some soils, this is also called the angle of repose. So if you've ever heard that term, that's what they're referring to. So at that specific angle, you have a specific shear stress and specific normal stress. And so this would get into the point where soils will start to fail due to shear stress. So once again, when I was talking about clays being having high cohesion but zero friction, with clays, basically you're going to wind up with a slope that looks just like this, coming straight across, and so it basically is a horizontal line, and so you could do a bunch of different circles going across it just for different values for normal stress and shear stress. And then with something like sand, which is very has no cohesion, you're going to wind up with this line going right through here, and so what it's going to do is it's going to change your friction angle or angle of repose. So when we start talking about lateral earth pressure, this is kind of a big deal. So this is actually a building in China. And what happened was they didn't really consider lateral earth pressure too much. They were just wanting to get these buildings up. And so this building that's laying on its side looked equivalent to all the buildings you see around it. However, what was happening here is they were building a parking structure on the other side over here and then stacking all the excavated material over here against the river. And so what happened was it started raining really bad, and so all the pressure from this soil basically started pushing it out, and it basically sheared all the piles off, so this thing fell over right into the excavation. So this is one of the reasons I say it's very important to remember to consider lateral earth pressure. and it's a big deal. I mean, it toppled a 13-story building. So looking at lateral earth pressure, there's 3 types of lateral earth pressure. There's active, passive, and at rest. And so lateral earth pressure is basically the horizontal pressure applied by or to soil when it's against standing structures, i.e. buildings or retaining walls. And so looking at this diagram over here on the right, you'll see what active pressure is. Active pressure is basically trying to move the wall over here to the left, and passive pressure is basically trying to move the wall to the right. And so the deflected shape would basically move it over here. But then you have something called at-rest pressure. So if you have something that you're fairly certain will not move, like i.e. a foundation of a building or a basement wall or something like that, you could use what they call at-rest pressure and just assume it won't move. However, with retaining structures such as this, you have to consider active and passive stresses. Typically on the exam, what I've seen is there'll be a question where you have to use active and passive stresses, mainly because this is more complicated, so it kind of begs to differ. Why would you want a PE to do this when you could have them do this? Because if they can do this, they can surely do this question. So when we talk about it during these example problems, we'll be showing active and passive stress. So actually calculating lateral earth pressure requires the calculation of the coefficients. And so looking at lateral earth pressure at rest, we'll calculate K0, which becomes the effective vertical stress over the effective horizontal stress, which is roughly equivalent to 1 minus the sine of phi, or 1 minus the sine of the friction angle is the other way you can look at it. Then we also, if we're going to look at active and earth pressures, if we're not looking at any inclined backfill, we can use these 2 equations right here. And so for active, we have 1 minus the sine of phi divided by 1 plus the sine of phi. And so the exact opposite of that will be the passive earth pressure. And so if we plot these on a curve, with this being the friction angle phi, looking at it at 0, they're all 1. However, as you increase the friction angle, your passive earth pressure or your passive earth pressure coefficient will increase exponentially. And so one reason I show you this is because at any given friction angle, your passive pressure coefficient will always be greater than your active. And so what that typically will wind up meaning towards on the back end of this is you may wind up having higher pressures on the passive side than you will on the active side. Or at the very least, you're going to wind up with a situation where it takes less material on the passive side to be equivalent to the active side, just simply because the coefficients are much higher. So this is kind of another diagram. So this graph, this is a disclaimer, assumes that the total stress is the same for each of the earth pressures. This is not realistic necessarily, however, passive pressure is typically the largest. So basically what I'm getting at here is if I have a retaining wall and the wall goes right down the middle and I have the same exact soil materials on both sides, then yeah, you could potentially say this. However, typically with the vertical stress, since the soil profile is much lower on the passive side, i.e. that's why you would have a retaining wall, then you can't really say this. However, if I had a retaining wall with the same soil and the same height on both sides, then yeah, you could do this. But essentially all this is saying is that the stress for the active side is going to wind up being less than the stress on the passive side. And so for this problem, we want to just find the resultant active and passive forces. And so if you notice, I do have an incline right here on the backfill side of the active piece. And so that's going to change our coefficient calculation. And so this is kind of what the stress distribution would actually look like for the inclined section. Because it's inclined, it's going to change the way the pressure distribution actually goes for it. So what you're going to do is you're going to have this triangle distribution right here. And so the triangle is basically going to allow the resultant force, the active force, to be at a certain angle, and the angle will be equivalent to the backfill angle of 15 degrees. However, if you notice on the passive side, since the passive side is not inclined, we don't actually incline this one as well. And so with the triangle, the actual reaction or location of the resultant will be at the 2/3 point, or a third from the bottom. And so for here, this is 5 feet tall, and so this becomes 5/3 right here. And so that would be the height from the bottom for the passive force. So to actually calculate the active coefficient, we have to use a different equation. And if you look in the CE review manual or into the all-in-one handbook, you'll find these equations. This is the equation that you'll use for the active coefficient with an actual sloped backfill. So if I actually go through and calculate this using the 15 degrees, I wind up with an active coefficient of 0.31076. And then for the passive coefficient, I'll just use the standard friction angle and calculate the passive as 3.5371. However, one thing I do want to mention is if there was actually a friction here between the wall and the soil, you wouldn't be able to use the Rankine method anymore. You'd have to use the Coulomb method. So if this value right here is anything other than 0, you'd automatically have to use the Coulomb. The Rankine kind of just makes this assumption to basically simplifies this equation. So I didn't show this because it really wouldn't have changed anything too much other than you'd use some different equations and have another variable in here. So I just kind of assumed if it comes up on the test, you can look at the equation in the book. So if you got this method down, it's not too much more to get the next method. So to actually calculate this force right here, we're going to wind up with 1/2 times the unit weight times our coefficient times our height. And so PA is 8,079.76 pounds per foot. Once again, this pounds per foot is assuming the wall is of infinite length. And so this will be happening every foot along the wall. And so the pressure resisting that is 5,747.79 pounds per foot. So there's a bit of a disparity there. And that's something that when you were designing this, you would have to look at to make sure the wall didn't overturn. One thing I will say is I didn't actually convert this force, and so this is still based at this 15-degree angle. So you'd have to bring this down to figure out what the vertical and horizontal forces actually are.